Right, let's work on these problems from section chapter 3, section 5, related rate problems. Number 1 on that was gravel being dumped from a conveyor belt at a rate of 10 cubic feet per minute. Forms a pile shaped in a right circular cone. And one of the things they say is draw a picture. There's a right circular cone. Here's the conveyor belt. It's dumping the gravel onto the pile. Right circular cone whose base diameter and height are always the same. So the base diameter, D, is also equal to the height. So H equals D. Okay. And how fast is the height? So we want a function that has H in it. When the pile is 23 feet high, recall that the volume with a height h and a radius r is this. So the volume is 1/3 pi r squared h. They want to know how fast h is changing when v is changing. I think we call the volume how fast the height is increasing. So now we need to go back through and look at what do we have in here. So dump from the conveyor belt at a rate of 10 cubic feet volume per minute. Volume per time. So that's the change in the volume over the change in time is 10 feet cubed per minute. And what else do we know? We want to do it when it's 23 feet high, but how fast is the height changing? So that's dh dt. That's the changing. How fast is the height of the pile increasing? So the pile is going to be increasing, so we want to find dh dt. So we have this. It has two variables. We'd like to have it just one. They say the diameter and the height are the same, but the diameter is two radiuses, two radii, so that's 2r. The height is 2r, which means r is half of h. So that's what we can put in for the r. So, and then we would end up with an equation, pi h squared over 4, squaring the radius, times the height. Now we have a function that relates volume to the height. Let's simplify this a little bit. So this would be pi over 12 h cubed. Now in related rates, there's no time involved in this, it appears, in this equation, but we're taking the derivative with respect to time. So our independent variable is time. So when we take the derivative of v, we would get 1 times the derivative of however v relates to time, so it's going to be 1 dv dt. The chain rule says if we're taking a derivative with respect to time, then we have to take the derivative of the inside, which is dv dt. Like we did in implicit differentiation, where we had maybe x squared plus y squared equals 6 or something. When we took the derivative with respect to x, this became 2x, and derivative of x with respect to x is 1. However, on the y, we said this is 2y, but then we have to take the derivative of the inside, and that's not x, so it becomes dy dx. This would have been dx dx, which is 1. So that's what we're, same kind of idea here. When we're taking the derivative with respect to time, we have to add on, since this variable V is not t, and h is not with t. We have to put that in. So we got pi over 12, the constant, times 3h squared. The variable is not t, so we have to add dh dt. So this creates a relationship between the change in volume and the change in height, which is what they wanted to know. And there's still an h in this because the derivative of h to the third is 3h squared, and so that's why they said do this now at the specific moment when the height is 23. So now the volume is changing by 10 feet cubed per minute, and we have equals pi over 12 times 3. That would reduce the 12 to a 4. H, which they said 23 feet high, and we're going to square that, dh dt. So then when we divide both sides by this value to figure out what this is, we're going to have feet squared dividing into feet cubed, and our units will be feet per minute, which should be the units for the change in the height, which is in feet, over the change in time, which would be in minutes. So our answer is going to be 10 divided by pi over 4, 23 squared, and the units would be feet per minute. And pulling out the calculator here, let's see what that number turns out to be. 10 divided by parenthesis pi times 23 squared divided by 4 close parenthesis. Oop, I didn't get pi. Pi times 23 squared divided by 4. Enter. And I get it. The height changing at 0.024 feet per minute. 0.024 feet per minute. Okay. Number 2. A street light is at the top of a 13-foot tall pole. So I'm going to make a pole here, say it's 13 feet, and there's a light. Some sort of light up here. 13-foot pole, so that's not changing, so I can use that number. A 12-foot tall woman, or 6-foot tall, I don't know where I got 12, 6-foot tall woman that's not changing. Walks away from the pole, so that will be changing at a speed of 6 feet per second, so that's a change, and that's in this x, so dx dt is 6 feet per second. So that's how fast that is changing. So she's walking away, she's moving in that direction. How fast is the tip of her shadow moving? So the shadow is going to be caused by her body, which is going to be straight line out here onto the presumably straight ground. And so the shadow would be maybe y. And what we're trying to find then is dy dt. That makes sense? So how fast is the tip of her shadow moving? So how fast is this spot moving as she walks? Some speed here, the shadow's going to move. When she's close, is not going to move very fast, but when it's moving out here, it's going to have to move real fast. So, I think we have all the things here. Now we have to look for some sort of relationship that we might see in this problem. Well, it looks like we're seeing triangles. For instance, I see this triangle and a similar one here. So I can set up ratios of sides. Now, my variables are y and x, and neither one of those is directly on the triangle, but this one could be called y minus x, couldn't it? So if I do the ratio of y minus x, this side on the top would match the long one on the big triangle to y, would match up with 6 on the small triangle to 13 on the big triangle. Now it looks like I should multiply both sides by y, and I get y minus x equals 6y over 13, and I could multiply both sides by 13 just to make no fractions involved here, and I get 13y minus 13x equals 6y. So I could subtract 6y from both sides and add 13x to both sides, and I can now solve for x or y. But I need a relationship, and this would create a relationship between x and y, and that's all I need. And so now I need to find the relationship for dy dt and dx dt, which I can take the derivative of this with respect to time, because I want time as the independent variable. So the derivative of 7y is just 7, and since it's not t, we have to go dy dt equals 13 times the derivative of x with respect to t is dx dt. And now they said dx dt, she's walking at 6 feet per second, so that would be 6 here. Times 13 would equal 7 times dy dt, and that's what they want to know, is how fast the shadow's moving. So I divide by 7 on both sides, and I would get my answer to be 13 times 6 divided by 7, and I get that the shadow is moving at 11.142 feet per second. Okay, number 3. Now we have a leaking conical tank. Water's leaking out of an inverted, so that's an upside down cone, tank at a rate of 9600 cubic meters or cubic centimeters per minute. So this is a rate, and cubic centimeters is volume, so this is dV dt. At the same time, water is being pumped into the tank at a constant rate of 7. Let's see, no. Water, at the same time, water is being pumped into the tank at a constant rate. So there's another change in volume that's happening here. So it's the total volume is we're losing this much and we're gaining some amount of volume. dV, no, better not say that. So there is the rate that the water is going in. So let's just leave that for a sec. The tank has a height of 7 meters. That doesn't change, so I don't need to put a variable. The diameter of the top is 5 meters, so it's 5 meters clear across. The water level is rising, so there's water in the tank, and it's rising. So if I say this is h for height and is changing, then dH dt is equal to 22.0 centimeters per minute when the height is at 1.5. Well, 1.5 is going to be changing, so we don't want to use that in our stuff until we have the relationship between dH dt and dV dt. This is how the volume is changing because of the leak, but it's not all of the volume changing. So this is not true to say that that's the change in the volume. Okay? So, what's the relationship here? Well, the volume of the water that's in there is 1/3, because it's a cone. Area of the base, well, that's changing. The radius is changing, so I'm going to put an r in there. 1/3 pi r squared times h. Two variables over in the side here, and we got this one. We don't want to have both of them. We want to talk about how the height is changing. So we'd like to get r out of here. Okay, so what's the relationship? Well, the cone has a shape, and so does the water that sits in the cone, and they are proportional. So I should be able to do something with similar triangles here, where the radius of the top of the tank would be 2.5 meters. So I'll put my r's and h on top. So r is to 2.5 as h is to 7. And you can see that in this triangles in here. R to 2.5 is h is to 7. And I can let's see, I need to solve for r so that my relationship will have an h in it. So r would be 2.5 times h over 7. So my volume equation becomes 1/3 pi 2.5 h over 7 is r, and we've got to square that, times h. So this is 1/3 pi 2.5 squared over 7 squared times h squared times h to the 3rd. So now I'm going to take the derivative with respect to time because I now have a relationship has V and H related. And that's what I need to be able to do a comparison between dH dt and dV dt. So this becomes dV dt, because the derivative of V is 1 times the derivative of the inside is dV dt, equals, and I have all of this constant here, that's going to stick around, 1/3 pi 2.5 squared over 7 squared times the derivative of h to the third, which is 3h squared. Since it's not t, we have to go dh dt. And this 3 will cancel that 3, and so we'd have pi times this stuff, h squared dh dt. Now, they told us how much dH dt was. That's 22.0 centimeters per minute. And they told us to do this at when the height was, what was it? When the height of the water is 1.5. So we got to put 1.5 in there. So I'm going to have pi times 2.5 squared over 7 squared times 1.5 meters squared. 1.5 meters. Ooh, we better fix that because we're doing everything in centimeters here. These were in meters, but that doesn't matter because that's just proportional. The ratios cancel the meters out, so we need to make this not 1.5, but there's 100 centimeters in a meter, so this is got to be times 100, which makes it 1,550 squared. Then that will be the change in the volume of the tank. So, working that out, sorry I had that off the screen there. So, and it was 1.5 meters for the height of the tank, and we need to have it in centimeters, so we had to multiply the 1.5 times 100. So I have pi times 2.5 squared divided by 7 squared times 150 squared times 22, and I get the volume is changing by 198,353 centimeters cubed per minute. Now, it said the leak was taking out of it. This is how much the volume of this is changing. If the water level is rising, so it's gaining. So this is how fast it's rising, and so there's the amount that's being added, the water added, and minus the leak is how much water is causing the rise. And so we have to take the leak, which was this 9,600, and add it to this to know how much water is being added to keep up with the leak and cause it to rise. So we have to add plus 9,600 and we get the water must be added at 207,953 centimeters cubed per minute. Okay, you have to watch your units on this one because it had that 1.5 meters here. These meters canceled out because you get 2.5 meters over 7 meters, and the meters are canceling out when you do this. Okay, that was number 3. Number 4. A sailboat is at rest near its dock. A rope is attached to the bow of the boat, is drawn over a pulley on a post. At the end of the dock that is 5 feet higher than the bow. So this doesn't change, so I can use that. If the rope is being pulled in, so this is the length of the rope, let's call it X, so then the rate that's being pulled in would be a dx dt at 2 feet per minute. How fast is the boat approaching the dock? Well, that would be this, and so they want to know dy dt. I just arbitrarily assigned y to that. And they said when the length of the rope is 13, so that's a specific time, that's changing, so we can't use that when we set up the relationship. But clearly we have a right triangle here. So 5 squared plus y squared equals x squared. I have a relationship between x and y, so I can take the derivative with respect to time. Derivative of 25 is 0. Derivative of 2y of y squared is 2y dy dt, since we're taking it with respect to time, equals, an x squared would be 2x dx dt, since we're taking it with respect to time. They told us that dx dt was 2, and they said to do it when it was 13 feet, so we're going to put in 13 here for a specific time. And we have to find y at that specific time. So with x is 13 and this is 5, what would y be when this is 13 feet long? So we have to figure that specific time. 13 squared is 169, 25 squared is 25, so we take away the 25 and we get 144. So y would be 12 feet when this is 13 feet. So we're going to put 12 in there. So we get 24 dy dt equals 26 dx dt, but dx dt was 2, so I have 52 divided by 24 is dy dt. 52 divided by 24, and it would be feet per minute. Two 2.167 feet per minute is how fast the boat is moving towards the dock when that's happening. Next one we have is a swimming pool. And it's a little bit challenging to look at this, but the pool is 60 feet this way. This is the top. 20 feet wide, 25 feet wide. Neither of those are changing, so we can use those numbers. And its depth varies uniformly from 3 feet deep at this end to 15 feet deep at this end, as shown in the figure. And I presume they're putting water in this. So I see a triangle on this end, and I see a triangle that matches here. Where on this red, the triangle would be 3 less than 15 or 12 feet, and this side is 60 feet. And so I've got a triangle here that's going to be proportional to this one that's changing, which I can call this maybe X and Y or H and something, whatever. And suppose the pool is being emptied, has been emptied, and is now being filled with water at a rate of 800 cubic feet per minute. So that's a dV, cubic feet per minute, dt. At what rate is the depth, I'm calling that x, and so they want the rate, so they want how dx dt, the rate of the depth measured at its deepest point in the pool, increasing when it is 5 feet deep. Well, the when it's 5 is only at a specific time, so don't get used to the 5 right now. I've got to hang on to that 5 feet. When 5 feet, but that's changing. I need a relationship between the volume and x. Well, the volume is going to be a shape like this. And some of you might say, I don't know how to do that. Well, it's just think this is just half of a box, isn't it? They just chop off the bottom half. It's half of that. So the volume would be 1/2 length times width times, well, whatever that one is. So we got 1/2 x times y times 25. Okay, we've got two variables over here. We'd love to have just the x, so we want to find y in terms of x. And that's where we're going to use those triangles I saw early on. Let's see, x is to 12, not the height of the pool, but the height of this triangle that on the slopey part, is y to 60. So I want to get rid of the y, so I'm going to multiply both sides by 60. And 60 divided by 12 is 5, so 5x equals y. And I'll put that in here, so I get v is 1/2 times x times 5x, so 5x squared times 25. So now if I take the derivative, I get dv dt equals, the 2 comes down and multiplies, we'll cancel a half, and it'll be 5 times 25 is 125 x to the 1, and the 2 canceled the half, dx dt. And so they want to know this when this was 5 feet and the volume is changing at 800. So I have 600 equals 5 times 125 is 625 dx dt. So I got to divide 800 by 625, and I get 1.28 and that would be feet per minute is how fast the height is changing with respect to time. Number 6. A baseball diamond is a square, and we usually do it this way. That's just the way baseball players like to draw it with a home plate down here, and a first base, second base, third base, for those of you who are not familiar with baseball. And each side is 90 feet. That doesn't change. So we can put that on there. Suppose a baseball player is advancing from second to third at a rate. So we got this person running down the line here this way towards third at a rate of, so we need an X on this thing. So I'm going to draw, I'm going to call this the distance left to run, X, and so I'd have dx dt running down the line at 24 feet per second. And the umpire is standing at home plate. That's him down here. The angle theta, let it be the angle between the third base line and the line of sight from the umpire to the runner. Line of sight to the runner and the third base, the line between the third baseline, which is this one. So this is the angle that they want us to do, and they want us to find out how fast is theta changing. So they want d theta dt. So we need a relationship between x and theta. X is here, this is 90, this is theta. So I believe that the opposite over the adjacent, the tangent of theta, would be x divided by 90. Hence then I can take the derivative of this with respect to time. The derivative of tangent is secant squared theta d theta dt, because we're doing it with respect to time, would equal, this is 1/90th, and the derivative of x is 1 dx dt. And when the runner is 30 feet, so that's a specific thing, that's changing. So we don't use the 30 until now. We've got the relationship, and now we use the 30. So I want to solve for d theta dt, so I'm going to, this is 1 over cosine squared, so I'm going to multiply both sides by cosine squared, so I get d theta dt equals cosine squared theta over 90 dx dt. This is 1 over cosine squared, so I'm going to multiply by cosine squared theta, which would cancel this, and cosine squared theta. So What they want is d theta dt, and it's going to be the cosine of this angle. Cosine is adjacent over the hypotenuse. So the hypotenuse would be 30 squared plus 90 squared, square root. So the cosine would be 90 over that, and squared would get rid of the square root, so I'd have 90 squared over 30 squared plus 90 squared, that's the cosine squared, divided by 90 dx dt, but dx dt was 24, so we got this times 24, and that'll be d theta dt. So this 90 will cancel one of these 90, so I have 90 times 24 divided by parenthesis 30 squared plus 90 squared. And I get 0.24 radians, angle measured in radians, per the time was measured in seconds. So the angle is changing by 0.24, or roughly a quarter of a radian per second. And finally, sand is being dumped onto a pile from a conveyor belt in such a way that a pile forms the shape of a cone. You can see that this is a popular type of problem, so it's falling onto the cone. Forms a cone whose radius is always equal to the height, so the radius and the height are the same. Assuming the sand is being dumped at 10 cubic feet per minute, so that's dV dt is 10 feet cubed per minute. How fast is the height pile changing when there are 1,000 cubic feet in the pile? Well, that's a little different than what we've had before. 1,000 feet cubed equals the volume. So what's the relationship here? Well, the volume of the sand is 1/3 pi r squared h, and we need to do this, and they want to know how fast the height is changing, so we'd like to have h's, and since r and h are the same, we could call this 1/3 pi h cubed is the volume. Taking the derivative with respect to time, dv dt would equal 3 would come down, cancel that, so it'd be pi h squared dh dt, which is what they wanted to know, how fast the height is changing. The volume is changing by 10, but we need to know h for at a particular time, and so they want to know when the volume is this. So we're going to write this is equal to the 1/3 pi h cubed is equal to 1,000, and solve for h at this particular time. So I'm going to multiply by 3 and divide by pi. So I'm going to get 3,000 divided by pi, and then I got to take the cube root to find h. To the 1 divided by 3 power, cube root. So h would have been 9.847 feet when the volume is 1,000. So I've used that in for my h, square it. Take it times pi. And then take it times d, and that's this number, and this is 10, so I got to divide this 10 by this. So I got to take 10 divided by that answer, and I get that the height is changing at 0.3032 feet per minute.